All right, let's talk about one of the most important ideas in all of chemistry. Something that sounds a little weird, maybe even a little intimidating. The mole. We're going to break it down and see how chemists figured out a way to count things that are literally impossible to see.
So here's the thing. At its heart, chemistry is all about atoms bumping into each other and rearranging. It's a numbers game. But the problem is, atoms are just ridiculously, unbelievably tiny. You can't just, pick them up and count them. So, how in the world do you keep track of them?
Take a look at this. You've got some iron powder, some sulfur, a bunch of coins, and some nails. Now, if I ask you which one of these piles has the most individual things in it, could you tell me just by weighing them? No way. A heavy pile of big nails is definitely going to have fewer items than a lighter pile of teeny tiny sulfur crystals. And that, right there, is the exact same problem chemists face every single day. Weight alone just doesn't tell you the count.
So how did chemists get around this? Well, with a pretty simple and honestly a brilliant idea that we can basically think of as a chemist's dozen. I mean, think about it. We do this all the time. You don't ask for 12 eggs, you ask for a dozen eggs. You don't ask for 500 sheets of paper, you ask for a ream. They're just convenient words for a specific number. Well, chemists needed the same kind of shortcut. Except because they're dealing with trillions upon trillions of atoms at a time, they needed a counting unit that was, well, a really, really big one. And here it is, side by side. A dozen means 12 things. A mole means 6.022 times 10 to the 23rd things. That's it. It's just a word that stands for a number. And just to be clear, it has nothing to do with the little furry animal that digs up your lawn. It's just a name for a quantity, like dozen or couple or trio.
Okay, so here's the official definition. A mole is a counting unit that represents 6.022 times 10 to the 23rd particles. And that ginormous number, it gets its own special name, Avogadro's number. So from now on, whenever you hear the word mole in chemistry, I want your brain to just think, okay, that's just a specific, ridiculously large number of things.
And just to give you a sense of the scale we are talking about, here's Avogadro's number written out. That is 602.2 sextillion. It's a number so big it's almost impossible to wrap your head around, but it's exactly the right size to make counting atoms something we can actually do.
All right, so a mole is a number. We've got that. But that still doesn't totally solve our problem, does it? We still can't see the atoms to count out a mole of them. And this is where the next really clever piece of the puzzle comes in, connecting that count to something we can measure in the lab, which is mass.
This really is the million-dollar question. How much does a mole weigh? Well, think back to our dozen. If I ask, how much does a dozen weigh? Your answer would be, a dozen of what? A dozen bowling balls weighs a whole lot more than a dozen feathers. It's exactly the same with atoms. A mole of heavy gold atoms is going to weigh a lot more than a mole of light carbon atoms. And this leads us to our next big idea, molar mass. All molar mass is the mass in grams of 1 mole of a substance. And this is the magic bridge. It's the connection between the invisible world of counting atoms and the very visible, very real world of weighing things on a scale. Now, this is where the whole system becomes so elegant. It's beautiful, really. If you look up carbon on a periodic table, you'll see its atomic mass is about 12 atomic mass units, or AMU. Well, guess what its molar mass is? 12 grams per mole. Gold has an atomic mass of about 197 AMU. Its molar mass? 197 grams per mole. The number is the same. Now, that's not a coincidence. It's the genius of the design. Avogadro's number was specifically chosen to make this perfect one-to-one link.
So now we have our two key tools. We have our counting unit, the mole, and we have our bridge from that count to a measurable weight, the molar mass. Now we can put them together and build a seriously powerful toolkit for solving problems. You can see it right here. These two ideas give us simple ways to convert between things. Avogadro's number is the bridge that takes us from moles to the actual number of atoms. Molar mass is the bridge that takes us from moles to mass in grams. The mole is right there in the middle. It's the central hub that connects everything together. Okay, let's put it into practice. Let's say you're in the lab and you weigh out 5.68 grams of gold. You want to know, how many moles is that? Easy. First, you grab your tool, the molar mass of gold from the periodic table, about 197 grams per mole. Then you just divide the mass you have by the mass of 1 mole. The grams cancel out, which is how you know you've set it up right, and boom, you're left with your answer, about 0.0288 moles of gold. We literally just counted atoms by weighing them.
And this really is the key point. This is what it all boils down to. The molar mass is the conversion factor. It's the special tool that lets us translate the language of grams, which we can measure, into the language of moles, which is the count.
And when you put the whole thing together, you get this amazing mole map. It's a flowchart for solving all kinds of chemistry problems. You can start with grams of a substance, convert that to moles, figure out the moles of just one element inside it, and even go back to find the grams of that element. It's an incredible roadmap.
So, we've gone through the definitions and seen how it all works. But let's just take a step back and really appreciate why this one idea is so incredibly important, why it's one of the absolute cornerstones of all chemistry.
So here's the bottom line. First, and most obviously, it lets us count atoms by weighing them, which solves our original problem. Second, it's what gives chemical formulas their real-world meaning. H2O isn't just about two tiny atoms. It's a recipe that says for every 1 mole of oxygen, you need 2 moles of hydrogen. This lets us be incredibly precise when we're mixing chemicals. And at the end of the day, that's what the mole really is. It's the essential connection between the invisible world of atoms and the visible, tangible world that we all work in.
So we've done it. We've figured out how to count the uncountable. We can take a scoop of some powder, put it on a scale, and know almost exactly how many atoms are sitting in that pile. Pretty amazing, right? So the big question is, now that we have this power, what happens next? What can we learn when we start mixing these counted piles together and watching them react? Well, that's a story for another time.